Okay, last chapter. We are on particle physics and cosmology. Where we're going to go today is we're going to take a look at fundamental particles. And what I mean by that is we have been lying to you a little bit in that we said we cannot split an atom up into smaller pieces. It turns out we can, and we actually get subatomic particles. So we'll explain briefly about how we can essentially split an atom open into these subatomic particles, how we can detect them, learn how they interact with each other, and how they can actually hold the atom together using things like the strong and weak nuclear force. One of the subatomic particles we'll talk about is a quark, so we'll talk about those and how they can form other particles. And then what we'll do is we'll kind of talk about conservation of some various properties of quarks and so on and so forth. And we'll kind of finish off by talking a little bit about the Big Bang Theory and with Hubble's law. So we'll start with just a brief history on fundamental particles, and I will also say that if you go on Wikipedia, the subatomic particle page is very readable. I know that sometimes Wikipedia pages can be very technical, but I thought that it was well worth your time checking it out. We've already talked about how we discovered the electron. That was J.J. Thomson. We've talked about how Einstein postulated the photon. And we talked about how Rutherford discovered the proton. But let's talk a little bit about the neutron. The neutron was actually discovered in the 1930s by two German physicists. And one problem with finding the neutron is that it's hard to detect. It doesn't have any charge, so it doesn't bend in a magnetic field, and it doesn't like to interact with electrons. And kind of the way that they discovered is that they had an alpha particle that they pumped into some beryllium, and it turned into carbon and then one neutron. And then the neutron could interact with boron, and it could generate an alpha particle, which we could then see. Now, another fundamental particle I want to talk about is called a positron. And essentially, a positron is going to be a particle that has the mass of an electron, but a positive charge, and the charge would be the same 1.6 times 10 to the negative 19th that you would find on a traditional electron. So let's talk a little bit about the history of the positron. In 1928, a fellow by the name of Dirac, and he shows up a lot in higher level physics, he solved Schrodinger's equations, and what he kind of found is he found that there's going to be some positive energy states, but there's also going to be some negative energy states, and he was trying to figure out what's up with that. And very typically we're used to taking an electron and popping up to a high energy state with a photon, and then it can drop back down. But what he kind of realized is, well, if we had a hole down here in one of the negative energy states, then that's going to act just like a positive charge. Now, he actually thought that it was going to be a proton, but the masses just didn't work out, and so it turned out to be this creature called a positron. And essentially, if we had a photon with twice the energy come in, it could actually essentially kick a positron up to an electron, and vice versa. If we had an electron that dropped down to that state right over there, it's going to emit two photons, and it has to emit two. It has to conserve energy, and it also has to conserve momentum. Remember that photons do have some momentum to them. In the 1930s, actually it was 1932, it was an American physicist who was looking at some of the radiation that is coming into Earth from space, and he had a lead plate just like this, and he had something called a cloud chamber, and what he observed was something kind of come in just like this, and inside the cloud chamber there's some gases and, more importantly, a magnetic field, and he saw this little track right there, and the track went like this. And he said to himself, wait a minute, I know that the direction of my magnetic field, and I have my good friend from physics 242, Q is equal to V cross B. If this was an electron, I'd expect it to go in this direction right over here. So he actually called this thing a positron, and it did indeed have the mass of an electron and the charge of an electron, however positive. Now, keep in mind that positrons are huge, and I've been lying to you. I've said that matter cannot be created nor destroyed. However, matter can be created or destroyed, and an example of that is going to be pair production. And pair production is going to happen when we have some charged particles that collide, really high energy, by the way, and they're going to produce an electron and a positron. And More importantly, when an electron and a positron collide, they're going to destroy each other and they're going to release energy. So we actually say that's going to be the anti-particle of an electron because it can destroy it. We can see an electron-positron pair happening in a collision right over here, and we know that if we had an electron in a magnetic field, F is equal to Q V cross B, we know which direction it's going to go. So if we had a high energy photon come in like this, hit a plate, then the magnetic field is going to bend it because they have opposite charge but equal masses. You're going to see these guys go off in the same radii curve, however in different directions. You see this in this figure right here. How much energy? Well, it's actually going to be 2 times the mass energy, or the rest energy of an electron, and we very typically write this in rest energy, so it's going to be E divided by C squared. So for an electron, really important, we're going to be using this guy a lot. The rest energy is going to be 0.511 mega electron volts per C squared. So in order for this to happen, this gamma ray would have to have twice that energy, which is going to be equal to 1.022 mega electron volts per C squared. And this guy's going to be important. You're going to see that guy quite a bit. Now, in the mid-1930s, we were kind of figuring things out, especially about like the nuclear force, and we were wondering, what mediates the nuclear force? I mean, what kind of controls it? And let's just talk very quickly about the nuclear force in general. If we were to consider 2 negatively charged skaters, they can exert a force on each other by emitting a photon, a ball, and pushing back and forth on each other. But what would draw 2 oppositely charged particles together? Well, if you were to picture these guys both grabbing hold of the ball and pulling towards it, then they're going to have an attractive force, and this would be something more like the nuclear force. But what controls it? How slippery is the ball? It was a Japanese physicist in 1935 that came up with a particle called a meson, M-E-S-O-N, and he said that this guy is going to mediate the nuclear force, but on a really small scale. We're talking about 1.5 femtometers, so really small, and it drops off. It's going to have some potential, just like the Coulomb potential does, and it's going to drop off a whole heck of a lot faster than the Coulomb potential does. It will only act at really small distances. A little bit later, it was a couple of people were studying cosmic radiation, and they came up with 2 other particles that could mediate this force, and they called them muons, M-U-O-N-S, and one of them they called the mu negative, and it had a charge equal to an electron, and it had an antiparticle that we have a plus right on there, and it has a positive charge. They both had equal mass, and it works out to be about 207 times the mass of an electron. A little bit later, about the 1947 or so, we discovered another form of a meson, and it was called the pi mesons, or also known as the pions, P-I-O-N-S, and they had charges of plus E, minus E, and 0, and these guys had masses that were about 270 times the mass of an electron. So we're discovering all of these subatomic particles. Now I will come back and talk about these particles a little bit, but let's talk about how we detect them. Usually we use a particle accelerator, and you could have a linear one or you could have a cyclotron, and these guys essentially can have a source, and this source is going to emit some particles, and then we're going to accelerate it. We're going to accelerate it using a high frequency alternating voltage, and we know our good old friend F is equal to QE from physics 242, and so as this thing goes through these guys, which are actually called leads, it's going to start to accelerate it, but we want to be able to accelerate it in a really small space, so we put in a magnetic field, and we know our good friend F is equal to Q V crossed with B. We realize that this force can do no work, however it can change the direction, so this thing is going to start to spiral, and as it goes from one lead to the other, the alternating part of the voltage is going to flip around so it can keep on accelerating in the same direction. The particle is going to spiral out like this, and it's going to have a huge amount of energy, and then we can smash it into something else when it comes out just right here, and it needs to be high energy because that's the way we can see these really high energy particles. Now, a couple of equations. Remember this guy from Physics 242? This kind of describes the radius that this guy is going to come flying out of the leaves at. It will have some angular speed. We can convert this guy to linear speed using some Physics 241, so it's all kind of coming together now. And this thing is going to have some kinetic energy related to its maximum speed, which we can kind of write as such. One thing to note is the angular speed that this guy has is actually going to be related to the high frequency voltage. So this right here, remember our good friend omega is equal to 2 pi multiplied by frequency. This is also going to be the frequency that the voltage is alternating. That's going to dictate kind of the speed. So let's just take a quick look at example 44.1. They built a cyclotron in the 1930s. That was relatively small, but hey, it was the 1930s. What can you do? It had a radius of half of a meter, and it had a magnetic field of 1.5 Tesla. And if we used it to accelerate protons, what frequency do we need to apply to the D's for the alternating current? And pretty straightforward. Frequency is going to be angular frequency divided by 2 pi. And angular frequency we can write as QB divided by m. Q is just the charge of an electron, and we have an absolute value because it's a positively charged particle. There's our magnetic field. 2 pi, don't forget we're using a proton here, so that's the mass of a proton, and it works out to be about 23 megahertz. Now we're looking for the maximum particle energy, and essentially just plug and chug into equation 44.8, and it's going to work itself out to be that many joules, or 27 mega electron volts. Keep in mind that this was the 1930s, and also if we were to have cyclotrons where we're not smashing a moving particle into a stationary particle, we can get more bang for our buck. And nowadays we're talking about colliders where we're in the tera electron volt range. Let's just consider for a second that we had a system where we have some particle that has some mass m, and it's initially at rest, and we go ahead and we smash something that has little m into it. It's going to release some energy. How much energy is available, and actually it's available to the center of momentum of the system, because this thing is going to start to move off in that direction right over there. It's just going to be essentially mc squared. So this is going to be the energy available to the system, and that includes the total rest energy of the system. So the rest mass energy is this guy right over here. So we're just adding mc squared, and mc squared. And let's just make it a little bit easier. Let's say that the masses are equal. You can convince yourself that this guy is going to boil down to this. Or if the energy of the particle that you're smashing into the big one is relatively small, then you can even just boil this guy down even further into this guy right here. And again, this is going to be the energy available to the system. It's kind of what you're smashing your thing into, as well as what you're bombarding it into. This example right here, just check it out and figure out, just take a look at the energies when we're smashing together a proton with one at rest. It's going to, both particles are going to survive the collision, giving up some energy, and a pion is going to escape. We have its energy. What threshold energy, what value of kinetic energy did we have to have for this process to occur? And then you can just gotta go ahead and convince yourself that it's going to boil down like this. And we know some rest energies of this pion, and it works out to be about 280